Good afternoon, everyone. We are enemies of syntax. We are a trio of active young citizens of the world trying to make the world a better place and ensuring the survival of our civilization. My teammates and I have always wanted an opportunity to contribute towards fighting climate change on a global scale, which has been provided to us today courtesy of Baker Hughes and Texas A&M University. Spreading the word out about global warming and following a strict recycling regime are helpful on a local scale, but a sustainable energy solution is what we need to implement this on a global scale. As we initially try to understand what Baker Hughes, an energy technology company, does, that is, work towards a cleaner, safer, and smarter future by doing what others don't and committing to what others won't, we realized that the first step towards a sustainable future lies not in implementing greener solutions, but by identifying and eliminating the worst carbon generators currently present in the world.
Hello, I'm Jayajin. So we basically chose Streamlit as a front end for the dashboard as it offers a really good UI and interactive features as you will see further. So for the beginning, the plant location navigation that basically shows us a geographical map that has the different plant site markers added to it. So what we did was we used the given coordinates in the site metadata CSV and using the latitudes and longitudes we added markers to them. Due to the time constraint, we couldn't add much more detail to them. We thought of adding elevation values and thermal efficiency values to them. So we could have improved the design and details over there, but due to time constraint, we couldn't. So that is that. And so the next was customer plants. Here, what we show is basically a bar graph of various customers along with the plants dedicated to them. So every customer has a plant dedicated to them, and every plant has engines of it. So busy and judicious customers had the most number of plants to them with values ranging up to 6. Moving on was plant site elevations. So this was quite a unique value as well as the chart we went for. So elevation, how elevation affects a plant site's efficiency is something like elevation of a plant site increases the air. As the elevation of plant site increases, the air density around it decreases. Hence, this forces the compressors to consume more power. This reduces the plant's efficiency, and so what we did was we plotted it on a PyDeck Python library chart. So it is basically a 3D library that offers a very good UI where height-based maps and values are quite evident. So the values of the elevations are not to scale because they are quite as they act as a reference to the rest around them. So it was quite evident that the company's Skeptical's Zircon Camel plant had the highest elevation of value 4067.59, and Delightful's Tourmaline mouse had the least elevation of value 14.4583. Next was the thermal efficiency. So the formula for thermal efficiency was given to us. It was the percentage of the ratio of power to flow fuel rate into fuel lower heating value. So the fuel overheating value was given in the metadata CSV, and the rest was the rest of the data values were given in an individual engine CSVs. So what we did was we first joined those engine CSV values for each plant, and then we added the powers because power is an additive quantity, and even the flow fuel, and then we took an average out of them. So that is how we calculated the thermal efficiency for each plant. And then we in the UI you can see that we have given them a quite interactive dashboard here. They can choose the plant names, they can choose the time duration, they can choose the period, daily, weekly, monthly. So that was our goal, and it was quite evident that spiritual polecat and prehistoric petrel had the best average thermal efficiency throughout the year. So that was the inference we got out of that. Then moving on, we have the N2 emission. The N2 emission here is a very responsive heat map. So we chose the heat map because it shows spreaded data values quite well. And to monitor the spread of these emissions, it was the UI is quite interactive. Here, the UI has many features like you can add markers or circles to take note of these regions that and take necessary actions further. So moving ahead was the operational hours. Now here we did have the formula, but we couldn't work much more on the UI. If we had time, we could have done that. But right now, we just calculated the operational hours for around a few stations. So we did get a values ranging from probably to 2,400 hours to 4,000 a few hours. So that was that. We chose the compressor speed and date time measures from the dataset to calculate operational hours. So yeah, so in all, we found that the first of all of the plant sites were quite spread in appropriate places, apart away from the residential areas, and but the only thing that we noticed was elevation values were quite rangy. The range of elevation values were quite long, from 14 to 4,000. That is a very spread out thing, and N2 emissions was good enough, but in some places, for example, if I could tell you, just like the Poyang country, Shanghai, GNK, China had N2 emission of 14.71, which affects the population of 69 lakh people. So that was one location that the station location that affects people. So yeah, that's about it. Thank you.